So geosynchronous orbit, as I said in the last example, is extremely important to things such as GPS satellites. It's important that those satellites stay in the exact same position at all times relative to the Earth. So we need to know exactly how far away from the Earth a geosynchronous orbit would be. So we have a 510 kilogram communication satellite. Now, I'll tell you this now, the mass of the object is not important. This could be 510 kilograms, it could be 5 kilograms, it could be 10,000 kilograms. That mass is not important. Geosynchronous orbit remains in the same relative position because it has a period of 24 hours, the exact same as the rotation of the Earth. And what is the radius of the satellite's orbit? Well, we need to know a few things before we do that. A geosynchronous orbit, the equation for it is RGO equals GMT squared over 4 pi squared to the power of 1/3. So to use this equation, we need to know G, which we can look it up as always, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. The mass that matters in this equation is the mass of the planet being orbited, so that's Earth. Looking that up, 5.98 times 10 to the 24th kilograms. T is the period of rotation of the satellite, which should be 24 hours. But we can't use hours in a calculation, we need seconds. So if we multiply that by 60, we'll find the number of minutes, and multiply that by 60 again, we'll get seconds, which works out to 86,400 seconds. And from here we can substitute in. G is 6.67 times 10 to the minus 11. M, 5.98 times 10 to the 24th. T, 86,400, that is squared. That's over 4 pi squared, all to the exponent of 1/3. This can be done in one stop in the calculator. We'll go to 3 sig figs, and we get 42,200,000 meters. Again, this is more commonly referred to in kilometers, so dividing that by 1,000, we would get 42,200 kilometers. So every GPS satellite, every other satellite in a geosynchronous orbit is 42,200 kilometers up.